Well, hello everybody. What I need to do with you today is I need to continue our studies over the related rate problems. And what I need to do today is talk to you about how we handle related rate problems that deal with cones. Cones are special because every cone has a radius and every cone has a height. But as we think about the liquid or the substance inside the cone, whether we're filling it up, changing the volume, or draining it, notice that along the way, the radius keeps changing. And while the radius is changing, the heights are changing. So in a cone problem, you'll see a dV dt for the volume changing. You may see a dr dt, or you may see a dH dt. All depends on the problem. The key thing today on solving these cone problems, though, we always have to find a relationship between the radius and the height. I've got 3 examples coming your way, so you'll kind of see what I'm talking about there. So there's the answers to our related rate problems from last time. You can always pause the video here and look those over and come in for any help that you might have. Now, you will need the class examples in front of you, not for my first couple of examples, but for the first 3. So, let me get back to where I was. Okay. Now, some things that's going to show up today. You're going to see similar triangles today. Every cone has multiple similar triangles within there. And I just want to show you how we solve these as we go. If I want to figure out this value of x, these triangles are similar because they have this angle the same, they have that angle the same, and from your geometry days, these 2 triangles are similar because of angle. Now, when I set this up, I can do a couple of different things, but I'm going to say something like this. If I'd like to figure out the value of x, I'm going to say the radius of the cone. So I'm going to say 3 is to 8. This radius is to the height, as this radius is to the height. There's other ways to set this up also. You could say the little side of the triangle is to the little side of the triangle, as the medium side of the triangle is to the medium triangle side of the triangle. No matter what, we're going to solve these exactly the same. Notice that when I cross multiply, I would have 8x equal 3 times 18, and then we'd solve that for x. If we do it my original way, notice I'm going to have 8x equal 3 times 18, and then we'll go solve that for x. So you're going to see similar triangles today. The other thing that you're going to see some fancy algebra that looks like this. If r is equal to 1/2 h, and I will show you how to get that relationship within the problem. But if r equal 1/2 of h, find and simplify volume equal 1/3 pi r squared h. Well, all I'm going to do, guys, is I'm going to sub this r value right there. So it's going to look like this. I got volume equal 1/3 pi 1/2 h quantity squared times another h. Now when I simplify this, I've got 1/3 pi times 1/4 h squared times another h. If I simplify again, I've got 1/3 pi times 1/4 h cubed. Now, I could take this a step further. I could also say 1/3 times 1/4 is 1/12. We normally don't do that because within the problem we're going to be finding the volume. So, and to do that, we're going to find the derivative. So now, here goes your number 1. We're going to set this up a lot like we did last class on the related rates. It says grains pouring from a chute and forms a conical pile whose height and diameter are always the same. If you've ever helped with the harvest, you'll see a chute taking wheat to a pile, or you might see an auger dumping wheat on the ground. And what it does, it kind of starts off, but it just winds up being conical. That's where this example comes from. But, so here goes. It says grain poured from a chute forms a conical pile whose height and diameter are always the same. So one thing that I know my height is equal to my diameter, and since the diameter is 2 radii, I know my height can also be equal to twice my radius. So there's one thing so far. Now, it says if the height increases at a constant rate of 5 feet per minute, so something I know that dH dt is 5. At what rate is the sand pouring from the chute when the pile is 10 feet high? To figure out what we're looking for here, anytime you're pouring something in, pouring something out, drinking, dumping, you're changing the volume. So, at what rate is the sand pouring from the chute? I would like to find dV dt, and I'd like to find that when H is 10. So, there's my information that I'm going to be working with. Kind of just like we did last time. Now, the formula for the day, formula for the volume of a cone, volume equal 1/3 pi r squared h. The pi r squared h should look familiar. That's the volume of a cylinder. Multiply it by 1/3, you got the volume for a cone. Now here's the key thing on beating cone problems. I've got an R and an H. Very seldom will you ever be given a dr dt, a dH dt, a R, and an H. So I have to find a relationship between R and H. We have to decide if we want to keep, we need to decide if we want to keep R's in my formula or H's in my formula. So let's come back over here and look at what we have and what we're finding. I have a dH dt. I also have a H equal 10. So I need to keep keep H's in my formula. So I need to keep the H's in my formula. And boy, that blurred together. So what I'm going to do is I'm going to come back over to my relationship formula, this one right here that gives me a relationship between the height and the radius. And I'm going to solve this formula for R. So I'm going to have R equal 1/2 H. Now guys, the reason I solve for R, I'm going to take this information and plug it in right there. After I simplify then, look at what variable is going to be inside my formula. I'm going to have all H's. That's what I want in this case. So it's going to look like this. I've got volume equal 1/3 times pi times 1/2 H squared times another H. Now no calculus yet. We're simplifying this. Volume equal 1/3 pi. 1/2 H quantity squared is 1/4 H squared times another H. Now, I'm going to kind of simplify this, and I'll show you why. Volume equals 1/3 pi times 1/4 H cubed. I could multiply the 1/3 and the 1/4, but I don't need to. Look at what we're going to do next. We're going to find the derivative of this. Well, the 1/3, the pi, and the 1/4 are all constants. So I'm going to bring this 3 down. Well, look what happens with that 3 and that 1/3. They're going to cancel each other out. So when I find this derivative, I'm going to have dV dt is equal to 3 times 1/3, which cancels each other out. I'm left with 1/4 pi H squared dH dt. Now, we're just going to plug in our knowns. So, we're looking for dV dt. I've got 1/4. There's a pi in there. We're hollering stop. We're hollering pause. We're taking a picture when H is 10. So I now got 10 squared. And we were told that dH dt was 5. I'm going to clean off just a little area right here so I can write some answers since I'm running out of room. Now, when I run this through my calculator, I'm going to take 1/4 times 10 squared times 5, and then I'm going to add a pi with it. So my answer, dV dt, is going to be 125 times pi. My units is a volume unit, so I've got cubic feet per minute. So there goes. Guys, but the key thing on this cone problem is we need a relationship between the R and the H. If it's given to you, that's pretty nice. If it's not, we got to go find it. And then we sub it in, find the derivative, and plug in the numbers. Now, number 2 is a little bit different. So let's go over to your number 2. It says a conical water tank with a vertex down. So I'm going to draw you a beautiful little picture right here. So there's what I've got so far. A conical water tank with the vertex down has a radius of 10. So I'm going to come in and draw that, a radius of 10 at the top, and is 24 feet high. If water pours into the tank at a rate of 20 cubic feet per hour, this is a volume statement, and I know that for 2 reasons. We're pouring water into the tank, so we're changing whatever's inside. That's the volume. And if you look at your units, cubic feet is a volumes unit. So one thing that I know that dV dt is 20. It says, how fast is the depth of the water increasing? So we would like to find dH dt. And I'd like to find that when H is 16. Now, I'm going to start my problem a little bit here. I'm going to go ahead and go volume equal 1/3 pi r squared h. But now, guys, I need to get rid of either the r or the h. Now, in this case, I'm looking for a dH dt. I've got a h equals 16, so I would like to get rid of the r again. But we were not given a relationship between the radius and the height. When that happens, we have to go get one. So here's how we're going to go get one. I'm going to look at my original cone that has a original radius of 10 and a height of 24. And then I'm going to think throughout the problem. At some point, it has a radius, and at some other point, it has a height. Notice that they share this angle, and both of those are right angles, so I have similar triangles within there. So now here's what I'm going to do. I'm going to say 10 is to 24. The radius of the original cone is to the height of the original cone, as the radius at any time is to the height at any time. So there I've just kind of come up with a relationship between the radius and the height. I'm going to cross multiply at this moment, and then I'm going to pause. I'm going to say that 10 times h is equal to 24r. Now, let's go back and think for a second. Do we want to keep r's or h's in the formula? And we definitely want to keep the h's. So I'm going to solve this thing for r. So if I solve this for r, it looks like I have 10 r equal 10 over 24h, which is 5/12 h. Now I have a relationship that I like. R equal 5/12 h. Now what I'm going to do is I'm going to take this and plug it in right up here for r. So it's going to look like this. Volume equal 1/3 pi times r squared. So I got 5/12 h squared times another h. There should always be a h cubed or an r cubed in your problem. Let's simplify this. Volume equals 1/3 pi times 25 over 144 h cubed. So I squared the 5, I squared the 12, and did the h cubed. Now, believe it or not, we still haven't done any calculus yet. So now let's find the derivative. dV dt is, the 3 comes down and knocks out this 1/3. So I've got 25 over 144 pi h squared dh dt. Now let's plug in everything that we know. I know that dv dt is 20. I've got a 25 over 144. There's a pi. We're hollering stop. We're taking a picture of this when h is 16. So I've got 16 squared. And we're solving for dh dt. Now guys, the way I attack this now with my calculator, I'm going to go 25 divided by 144 times 16 squared. Whatever that number is, I'm going to go 20 divided by that number. So 25 divided by 144 times 16 squared, whatever number's on your calculator, I'm going to go 20 divided by that answer, math enter, and I'm going to get 9/20 at that moment. The only thing I haven't used is this pi right there. That's going to be in the denominator. So my answer is 9 over 20 pi, and my units is feet per hour. So there's the answer to that one. Now, one last one very, very similar to that. And then I'll be done with the cone part of it. I'll talk to you a little bit about some of your math Excel problems that's going to show up. So here goes my last one, kind of. A man is sipping a soda through a straw from a conical cup. So here's what I got so far. Here's my conical cup. That's 15 centimeters deep and 8 centimeters in diameter. So that means the radius is 4. So here goes. When the soda is 10 centimeters deep, so when h equals 10, he's drinking at a rate of 20 cubic centimeters per second. Notice the cubic again, so we're talking about volume. I know that dv dt is negative 20 because we're drinking it, right? How fast is a level of the soda dropping at that time? So we would like to find dh dt. Now, notice this. At no point within this problem were we given a relationship between the radius and the height. So we got to go get one real fast. So I'm going to say once again, the original radius is to the original height as the radius at any time is to the height at any time. Now, I'm going to cross multiply, so I've got 4h equal 15r. Now, let me come up and start looking at the formula. Volume equal 1/3 pi r squared h. Once again, we need to decide if we want h's in our formula or r's in our formula. Well, once again, I've got a h. I'm looking for dh dt, so we want to keep the h. So that means I need to solve this for r. And if I do that, it looks like r equal 4 over 15 times h. Well, still no calculus yet, guys. So volume equal 1/3 pi times 4/15 h squared times another h. Volume equals 1/3 pi times 16 over 225 h cubed. Let's go find our derivative now. So I'm going to have dv dt. Bring down my 3, cancels out that 1/3 again. So I've got 16 over 225 pi h squared dh dt. Well, now let's plug in. Now let's plug in what we know. We know that dV dt is negative 20. I've got 16 over 225. Pi. We're hollering stop. We're taking a picture when the height is 10. And we're solving this for dH dt. Now, one more time. To solve this and keep it as a nice looking number, I'm going to go 16 divided by 225 times 100. Don't touch the pi. And then I'm going to go negative 20 divided by that number, math enter, enter, and I'm going to get dH dt to be negative 45 over 16. I'm going to put the pi where it belongs. And then my units, centimeters per second. So guys, that's the cone problems. Now, on the next couple of slides, I'm going to talk to you about a couple of problems that's going to show up on your Math Excel so they don't look strange to you. So, you can write this down if you would like. But here's what we got. Some lucky person, I snipped this off of their Math Excel assignment, so it's going to be their problem that I'm going to do for you. But here's what it's going to look like on Math Excel. You're going to see a couple of problems that look like this. Assume x and y are functions of t. Evaluate dy dt. So the t is for time. For 3xy minus 7x plus 4y cubed equal negative 84. With this conditions, dx dt is negative 16, x is 4, y is negative 2. I graphed this earlier. What a weird looking graph. It looks like this. Above the x-axis, comes down and goes through the point 4, negative 2, continues on, but then at some point, way up in like the 700s, it curves back around and does this. So here's what this problem is saying. We have a particle, we have an ant running along this graph. And it's asking this question. As I approach the point 4, 2, my x value is decreasing by 16. So I must be coming in this way. It's asking, what's your y value doing? So now, the math portion of this. See this 3xy? I have to take the derivative of that with respect to time, and I'm going to have to use the product rule on it. So the derivative of 3xy would be the derivative of 3x, which is going to be 3 dx dt, because we're doing this with respect to time. So I got the derivative of the first times the second, plus the first times the derivative of the second, which would be 1 dy dt, because the x value is changing and the y's value is changing, minus the derivative of 7x is 7 dx dt, plus 12y squared dy dt, and that's going to equal 0. Now the calculus portion's done. I'm going to sub in numbers for dx dt, x and y. So it's going to look like this now. I've got 3 times negative 16 times negative 2 plus 3 times my x value of 4. I don't know what dy dt is, minus 7 times dx dt, which is negative 16, plus 12 times 4 dy dt, equal 0. Now guys, what I've done from here, just to save time on the video, 3 times negative 16 times negative 2 is 96, plus 12y, plus 112, plus 48 dy dt equals 0. I combined this and got 208 and moved it to the right-hand side as negative. Then I divided everything by 12 plus 48, 60. So here's how the value of y is changing. As my particles approach in this point, my y value is dropping at negative 52/15 at that time. So you're going to see a couple of problems like that on Math Excel today. You're also going to see revenue, cost, and profit again. So I'll kind of roll on this a little bit just to show you. Find the rate of change of total revenue and cost and profit with respect to time. This would be one of those Part A, Part B, Part C kind of problems. Assume that R of X and C of X are in dollars. Well, to find the derivative of the revenue, it's going to look like this. D capital R dt, the derivative of the revenue, is going to be the derivative of 60x, which is 60 dx dt, since we're dealing with time again, minus 2 times a half is 1 x dx dt. Now we're ready to plug in our numbers. How's the revenue changing? So dr dt is going to be 60 times dx dt, which is 20, minus x, which they told me is 30, times dx dt, which is 20. So it looks like I've got 1,200 minus 600. So it looks like my revenue is changing by $600 a day. I would do that same thing with the cost equation. When I find the derivative of the cost, d capital C dt, the derivative of the cost with respect to time, is going to be 6 dx dt. The derivative of the 10 is 0. Looks like dc dt is going to be 6 times dx dt. So it looks like that's going to be $120 a day. And I won't fully go through this last one, but now I got to do the profit. So remember profit, guys, revenue minus the cost. So my profit equation, 60x minus 0.5x squared minus 6x minus 10, I distributed. My profit equation, negative 0.5x squared plus 54x minus 10. Now we can find the derivative like we did on these two parts and plug in our numbers. So guys, that's the cone problems along with some Math Excel problems. Assignment-wise, what we had, finish the problems on that worksheet. You had an additional 5 problems that deals with the cones. And then there's 10 problems, if memory serves me right, on Math Excel. So good luck. If you have any questions, get in and I'll get you straightened out.